In the last video, we looked at the graph g of x equals 1 minus x, the line there, and we let a be equal to 0 and determined the formula for the area function a sub g of x. And we got minus 1/2 x squared plus x. Here I've graphed them both together for you so you can see the line and the parabola on the same axes. Now let me write these functions here again. A sub g of x was equal to minus 1/2 x squared plus x, and g of x, the one we started with, was minus x plus 1. So you can see here that a sub g prime of x is equal to g of x. Or we could say that a sub g is, let me write a sentence, a sub g is an antiderivative of little g. We just discovered this and observed this. We haven't proved that this always is the case, but we see at least with these two that it is. So let's just, by way of review, let's look at the properties of a sub g, the antiderivative, and the corresponding properties of its derivative g. So let's see, if you look at the graph of a sub g, you see that it is rising up until x equals 1. So we could say that a sub g is increasing on the interval minus infinity 1. It is decreasing on the interval 1 infinity. Over the interval from x equals 1 on, the graph is falling as you move from left to right. The top point there at x equals 1, we could say that a sub g has a max at x equals 1, a stationary point that is a maximum. And concavity is another property of functions that you studied in Calculus 1, and we see that the graph of a sub g is concave down everywhere. So we could say concave down, and I could say, to be even more clear, on minus infinity, infinity, the entire real number line. Now think back to Calc 1, and you saw that if a function was increasing, its derivative was positive. And sure enough, from x equals up from minus infinity to 1, we see that g is above the x-axis. So we could say g of x is greater than 0. And on the interval 1 infinity, here out, we see that the graph of g lies below the x-axis, so g of x is less than 0. The max at x equals 1, well, a stationary point, we know that derivatives are 0, and sure enough, g of 1 is equal to 0. And for a graph that's concave down, we see that g is decreasing. You're probably remembering from Calc 1 that if a function's graph is concave down, its second derivative is negative. Well, if g is the derivative of a sub g, its derivative is negative, meaning that g is decreasing. So all of this fits into exactly what you learned in Calculus 1. Please review these relationships if you need to. Another thing that we have discussed in the context of a different function, that was yesterday in the last class, problems 21 through 28 on page 320. We looked at area functions of the same g of x, or the same f of x, using different anchors. In other words, using different values of a, the bottom limit of integration. And we saw that we got, in each case, we came up with a formula for the area function, and in each case we came up with a function when differentiated gave us the integrand. In other words, an antiderivative of g of x. Notice here, if a is 0, a is 1, a is negative 2, we come up with each time an area function whose derivative is minus x plus 1. Oh boy. You guys, I changed this, but I must have, I'm sorry. I'm going to change it right here. Let me go get a white. I don't want to do this over again. Alright, so this is minus 1/2 x squared plus x when a was 0. Now when a is 1, watch how I'll correct this. I want a sub g, the area function, has to be 0 at 1. I know this is minus 1/2 x squared, and this is plus x. And now to check the sign on 1/2, I'll plug in 1. I get minus 1/2 plus 1, so this has to be minus. I'm sorry. And if a is negative 2, we're going to get minus, if you find the area function, you'll get minus 1/2 x squared plus x, and we want the function to be 0 at negative 2, so this would be minus 2 plus 4, so that one's okay there. Sorry about that. I made the correction, but apparently I didn't save it correctly. So what I want you to notice in these examples is that we get each time, regardless of what anchor we use, what lower limit of integration, we just get area functions that differ by a constant. Each time we come up with an antiderivative of g. We're going to do a couple problems like the ones I'm assigning you for homework to hand in. All these problems are for is to make you comfortable with the notation and to see this function up here, to see this function as a function of x. It's not a function of t. This is the independent variable right here. So let's look at number 57. Suppose that the integral from 0 to x of f of t dt, we don't know what f is, but it's some function, and if we compute the area function of it, we get the sine of x squared. So the area from 0 to x under the curve is the sine of x squared. We're just given that. Now it says evaluate the integral from 0 to the square root of pi over 3 of f of t dt. Well, this notation fits exactly our definition here. 0 to x f of t dt. So x is the square root of pi over 3, and it will be the sine of the square root of pi over 3 squared is simply pi over 3, and the sine of pi over 3 is the square root of 3 over 2. Now in number 59, it doesn't look exactly like what we have there, but we'll use properties of integrals in order to write this in a different way that will make it fit this definition, because that's all we know, is that the integral from bottom limit 0 to an upper limit is the sine of that upper limit squared. So I'm going to rewrite this as, well, we need a 0 down there. We don't want minus pi over 4, so I'm going to use a property of integrals and write this as the integral from minus the square root of pi over 4 to 0 of f, I'm just going to put f, plus the integral from 0 to x of f. That's using one property of integrals. Well, now I know what this is. That I know. That's going to be the sine of x squared. But this still is not written in the form where I can use that definition. So I'm going to rewrite that as minus the integral, I want 0 on the bottom, not the top, to minus the square root of pi over 4 of f plus the integral from 0 to x of f. So I've used two properties of integrals in order to rewrite. Now I can use our definition given above. Minus the sine of the top limit squared is just pi over 4 plus the sine of x squared. And let's see, the sine of pi over 4 is the square root of 2 over 2, so this will be minus the square root of 2 over 2 plus the sine of x squared. Again, this is just to practice with the notation. You're going to be able to need to use your properties of integrals to make things fit what you're given in the problem. It's just like a puzzle. And these problems are not important in themselves. They're here to make you get comfortable with the definitions and the notation that we're using. Speaking of notation, I would like to just review on this last slide function composition, the notation that we use. Function composition, when you have a function f of x and g of x, f of g of x is f composed with g. Now, all I'm going to talk about is the notation to recognize function composition when we see it. Everyone is really good at recognizing if I tell you that f of x is equal to the square root of x, and then I give you some function, let's say the square root of x squared plus 1, you're all going to tell me, oh, that's f of g of x, the square root of g of x, where g of x is equal to x squared plus 1. I think everybody's good at that. You've been doing that for years. But now, what if I tell you that h of x, let's say, capital H of x, is the integral from 1 to x of, it doesn't matter what I put here. Let's say sine t dt. Wouldn't want to use x there because x is the independent variable of this function. So we can't use it in two different ways. Okay, so now what I want you to recognize is, what if I give you this function? What if I give you the integral from 1 to 3x of sine t dt? Well, the argument, this is called the argument. The argument of a function is what's inside the parentheses here. The argument here is not x, it's 3x. So this is simply h of 3x. So I just want you to be sure that you can recognize something like that as function composition. And I think you probably already know why we would want to do that, because we're going to use the chain rule in differentiating things like this in section 5.3.